There was an endless amount of projects I could have done. I started with an RC car and how it operates, but then it didn't really catch my interest. Then I saw the 3D printed jellyfish on Instructables, and this was really interesting to me. I love to see how all the gears worked and how it moved, so that's what we landed on. Gear trains are also known as cogwheels, which is what I used in this project. The gears are used more on the traditional side of the gears that are more I used more pointed ones versus the other type. There are many types of gears, and this was the style I chose because I felt like it was a little more challenging and it made a more traditional gear block. Gears are simple machines. They are used to manipulate the magnitude and direction of the force. They also have a ratio of output force to input force, meaning that there is a ratio between the gears, and usually they're pretty similar. Usually when a gear is smaller than the other one, it moves faster or has more rotation than that of the bigger gear. For my project, I wanted smaller legs to move a little faster than the longer ones of the jellyfish, so I provided the longer legs with a slightly bigger gear, as shown. And the central gear is the biggest because it has the control of the motor, so that way it could evenly be dispersed for all eight legs and give it momentum. The relationship between the gears is dependent on the law of conservation of energy, which relates to the torque of each of the gears in their angular velocities. Gears usually have two purposes, and it's usually to increase the speed or the increase of force. One is usually not without the other. Alright, well that's enough about gears. Let's move on to the 3D printing. 3D printing is a great thing and it has many uses and can be applied in many ways and for many different things. I have only touched the surface on 3D printing as I am very new to it. You can make your parts in any way you want and with as much detail as you want, or you can print them from a pre-made file. You saw this in the gear making earlier that I was doing. 3D printing is not always easy. You don't always get it right the first time, or in my case, the fourth, fifth, and multiple times. However, I went through the process and tried to map out where things have gone wrong, and I think I finally got down to it. The filament I chose to have had a high point of heating, and it needed to be at 230 degrees versus the standard 200 degrees or 210 degrees. There were files that I could print from when I was for the jellyfish, which would have made this project much easier. But I wanted to create the thing myself. I wanted to have my own version of it, so I created everything on Onshape in respects to the Instructables version of this jellyfish. After I did that, I then put it into a slicing software, and that slicing software was Cura, and that made it ready for printing. I definitely had to do a lot more slicing, and it made me understand how 3D printers work with slicing a lot better. So now for the best part. Have you ever wondered why some jellyfish glow in the dark? Well, I wanted my jellyfish to glow in the dark. How do things glow in the dark? The simple answer is phosphorescence, which means light emitted by a substance without combustion or heat, basically. Now, this happens because of the absorption of energy. This is usually through an ultraviolet ray, and then it re-emits into the form of a visible light. Now, how does this happen? When exposed to light, the radiation, a shorter wavelength, the phosphorescent substance will glow and absorb the light and then re-emit it into a longer wavelength. On a simpler scale, electrons are on the lower energy level and are easily excited to a high level energy by electrons, then release their photons and return to the lower energy state. However, these electrons in the glowing material go through a change during the photon absorption. This prevents them the electrons to turning to a lower energy state normally and right away. It releases a photon a little at a time until it has reached the lower energy state. That's why it's really bright at first, and then it eventually goes down in light. Now, why is it blue or green? There's a lot of math behind that question, and I'll walk through the diagram of it. But first, here's the equations, and these equations each lead to why it's blue or green due to how blue is a different frequency than red in our visible light spectrum. And you can see that's why mine is blue or others are green. Even some can be like pink or orange. There's a lot of different reasons for that. But the equations are E equals hf, which is energy plus Planck's constant by the frequency of the radiation. And then we have another equation, C equals f lambda, which is the wavelength equation, and C is the speed of light. Now we kind of combine these two, and we get E equals hc over lambda. And that gives us our lambda, and our energy level we can find out, and then we can figure out the different frequencies at which is being emitted, and then you compare those to the scale on the light spectrum. So here is the level diagram. Okay. All right, so here we have an energy level diagram. In this diagram, we have a low and a high point. So up here's the high, and then down here's the low. And what's happening is we have a frequency coming in, a high frequency, a light ray, and it's exciting our electrons all the way up to our high level energy. And then what happens is it drops to a certain frequency, and then it can drop again to another frequency a little bit. And what happens is this top frequency emits more of a blue light like this, and our lower frequency lets out a red light like this, and that's what happens. This is why we get the green and the blue rays, because they're coming down from that excitement. So in this video, I tried out different types of light on my material, and each one did a little different due to the wavelengths on each of the lights. There is the normal light of the desk lamp, and then I used a normal flashlight that was LED, but it wasn't very strong, only about 100 looms. You can see this gives off a bit of light, but it's not super bright. Next, I used a black light of 365 nanometers of UV light. This had a more interesting reaction. It let the light spread out rather than a focal point where the light hit directly. It was the more effective. Next, I used a strong LED light of 450 looms. This had a reaction of a more focused light. You can see that directly when where the light was, and how it made it glow brighter and did not stay as long as when the UV or black light was hitting it. As shown after I did the higher powered light, it still had a strong glow than the LED light, the black. Now we saw that my filament glows blue, and this is because of the chemical composition of the phosphorus that was put into it, basically how it was made and why it glows blue rather than green like it did. Well, that's the end. I hope you all learned a little bit more about glow-in-the-dark materials and things that lead up to it, and that is it for my project. Thank you. Thanks for watching.